I feel a lot stronger because no pain, no gain.
All the departments continue to invest in innovative curriculum, qualified lecturers, and practical lab which close to the real working environment.
Our motto is committed to quality. Commitment is interpreted as a willingness to realize the goal of the institution in accordance with the up-to-date ability that must be aligned with attitude and behavior. Quality is interpreted as a standard that must always be updated because the needs and demands of stakeholders are always changing and dynamic. Quality is intended to motivate the performance of the elements in order to produce the relevance of the quality of graduates.
To make sure everything goes well, safety is the most important one. We have to wear personal protective equipment or PPE.
Quality is intended to motivate the performance of all elements in order to produce the relevance of the quality of graduate.
If we wear PPE, we can prevent accident because in here, SAFE stand for Stop Accident Forever. In polines, we learn something in details. We learn about marketing by organizing a mini market, so we know how to sell something in detail. We often learn about the bank system. It is about how to treat your customer, how can someone make their bank account, interest, and many more. And we also learn about how to type fast. Well, not just learning all day, because we have to interact with the others. And not just with the people around here, but we also have to interact with the foreigners.
Interesting practice in polines. For the examples like practical Islamic banking, because in there we not only know about the world of banking, but we can engage directly in the banking world. One of the most interesting practice, in my opinion, is financial audit. In our financial audit, we have to work as a team. And in a team, we must communicate well, calculate quickly, and the most important, to be precise. In polines, I also learned to get along to the others. There are various tribes and religions in here. We respect each other and we can enjoy together.
Students enjoy a balanced university life on vibrant campus with vibrant learning environment. There are are a variety of national and international events which contain a lot of cultural knowledge and cultural diversity in Indonesia.
We do hope committed to quality is not just a motto, but it can be understood by all elements in polines to motivate and inspire the realization of polines as technology and business innovation center. Well, polines can give a real contribution in the intellectual life of the nation and advance the welfare and competitiveness of the nation.
Halo, nama saya Sukaina. Saya berasal dari Belgia. Saya belajar di Polines di Prodi Management Business Internasional. Saya sudah berada di sini selama 4 bulan. Saya suka belajar di sini karena saya belajar budaya baru.
I think Indonesia is make me feel like at home because people are really familiar and just like friends of mine.
Polines committed to quality. I recommended this. Thank you.
There are also many students groups that connect every students with different interests to build their soft skills ability. Under the campus master plan to become leading vocational higher education, Polines try to commit and produce high quality graduates with relevance with global industries. Because Polines is committed to quality.
Hello, Professor Ku. Do you want to try to test sharing screen?
Okay, just hang on.
Please. Yes, it works. Do you have any video? Do you want to test?
Yes.
We couldn't hear the sound. Is there any sound?
Can you hear?
And cannot.
You cannot hear?
Yes.
There.
How about you, Mbak Ani? Can you hear the sound?
Can you hear?
I cannot hear the sound.
Oh, you cannot hear the sound. But here, I can hear very loud. Can you hear my voice?
Yeah, very low now. Maybe can you make it? Maybe.
Wait,
Yes, in here. Yes.
Can you hear?
Yes, here, but very low.
Low.
How about you, Mbak Ani?
Huh?
I can hear it, but it's kind of the sound is kind of low.
Can you hear?
Yeah, we can. I can hear. Yes.
But there's just music in the video.
Oh. Yes, we can hear.
Can you hear?
Yes. Okay. Oh. No, we cannot hear. Yeah, now we can hear.
Now can. But my side is very loud.
Yeah, it's okay. Okay.
Okay. After I will try to make it louder lah. Just one video. The rest no video.
Yeah. Okay. Thank you. Okay. Thank you. We still wait. Dr. Fazli, do you have a slide? Do you want to share as well?
Yes, certainly. Can I share my screen for a while?
Yes, please. Dr. Fazli, could you please turn on the video? We couldn't.
Okay, all right, hold on. Forgot to switch on my video. Hold on. Can you see me?
Yes, we
Okay.
can see you. And also the slide.
Okay, all right. You can see the slide, so I put it on slideshow.
Yes, please try.
Just a short presentation, so you can see
Okay.
clearly.
Yes. Perfect.
Okay, so
Do you have any video? Do you want to try?
Yes, I do. Hold on.
Ikon guest lecturer internasional ya. Wingi jadi diundang zaman Rebo wingi pas yang ketemu media kan. Selamat datang.
You can see the slides changing.
Is there any sound?
Can you hear any sound?
We couldn't hear.
Couldn't hear.
Same.
Can you hear?
Couldn't hear.
It's just music. There's nobody speaking within the video. It's just music.
Just music.
Can you hear anything?
I think they're very.
Cannot hear also.
Cannot hear.
Similar like just now when I play the video also. So Dr. Fazli, since you play this one, then I think my side I don't play the video lah, because I also plan to play the FET video, the one you sent to me.
This one is MMU video.
I'm
not showing the FET one.
So do you want me to play the FET video afterward?
Okay, can.
Can also.
Nah, this one is just an introductory to MMU.
Okay.
Can you hear anything? No.
We cannot hear. But it's fine.
There's something. You hear something. Okay, all right. Yes. Okay. All right. It should be okay now. So I'll stop sharing.
Okay, we will start in 2 minutes later.
Actually, already almost 500 participants registered, and now more than around 260, more than 260 already joined. Can we start now, Bani?
Is everyone ready? Pak Budi, are you ready?
Pak Budi, are you there? Yeah, I think Pak Budi is there.
Yeah. Sip.
Okay.
Shall we start now?
Yes.
Okay. Yeah.
All right. Good afternoon, ladies and gentlemen. Welcome to the International Case Lecture Series Graduate Competency Enhancement through International Case Lecture Series Electrical Engineering Department of Polytechnic Negeri Semarang. My name is Ani, and it's a wonderful and precious chance for me to be your Master of Ceremony in this event on Tuesday, 17th of November 2020. First of all, let's send thanks to God Almighty, who have been giving us guidance, happiness, health, and mercy, so we can attend and participate in this event. I would like to welcome Mr. Budi Prasetya as the Vice Director of Planning and Cooperation of Polytechnic Negeri Semarang. And then also like to welcome Associate Professor Dr. Fazli Saleh Abbas as the Dean of Faculty of Engineering and Technology, Multimedia University. Also would like to welcome Professor Dr. Ku Funchet from Multimedia University as today's speaker. Dr. Kurnia Ningsih from Electrical Engineering Department, Polytechnic Negeri Semarang as today's moderator. And also for all participants who is joining us today, welcome to you all. Before we start our lecture session, I would like to read today's rundown as follows. First agenda, we'll have an opening remark from Mr. Budi Prasetya, and then we'll have a greeting from Professor Dr. Fazli. Then we'll go to the next agenda is the presentation from the speaker that will be moderated by Dr. Kurnia Ningsih. And then we'll have a token appreciation, photo session, and lastly, closing remark. Without any further ado, let's start our first agenda, which is the opening remark from Mr. Budi Prasetya. Sir, time is yours.
Thank you, Ani. I'd like to most welcome our guest today. First of all, Associate Professor Dr. Fazli Saleh Abbas from the Dean Faculty of Engineering and Technology, Multimedia University. And then Professor Dr. Kyo Fonchet, here also from Multimedia University. And welcome to our fellow teachers from Polytechnic Negeri Semarang, Dr. Nia, Pak Kanto, and others, and distinguished guests and all of our participants today. Selamat siang. Assalamualaikum warahmatullahi wabarakatuh. Okay, we would like to extend our welcome and then also to express our deep gratitude and appreciations here to all faculties from Multimedia University, particularly the Dean, Dr. Fazli, and also our outstanding lecturers, Dr. Ko Funchet. So we would like to express our gratitude for joining us here in our international guest lecturer. And we do hope that we also have other cooperations in the future, not only attending the guest lecturer, but we do hope that we can have other collaborations such as exchanging lecturers or exchanging students and other programs that we would like to have in the coming year. Okay, so once again, thank you very much for your cooperations, Dr. Fazli and Dr. Ko Funchet. And we do also hope that today's lecturers on remote sensing with imaging radar has a lot of benefits for our students here particularly. So we hope that our students have more horizons, wider horizons, and also have a lot of knowledge by joining to this program. So once again, thank you very much for all your coming here to this guest lecture, and then we do hope that we have fruitful benefit that might be beneficial in the coming year. Okay, thank you very much for all. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Mr. Budi. Okay, our next agenda is the greeting speech from the Dean of Faculty of Engineering and Technology, Multimedia University, dear Associate Professor Dr. Fazli Saleh Ahbas. Time is yours, sir.
Thank you, Mrs. MC, Mrs. Chairman, Ms. Ani. And first of all, let me extend my gratitude and thanks to, first of all, Pak Budi, as the Vice Director of Planning for this event, and then Dr. Nia Kurniang Ningsih, the moderator for today's lecture series, and of course my colleague Prof. Kubun Chat, as well as all participants of this lecture series. And we feel very honored to be, first of all, invited by Dr. Nia to give or to deliver this lecture series. And since we signed an MOU with Polines last year, I think this is the first official event that we managed to organize together. So hopefully there'll be more and more events in the future. And of course, the situation with COVID-19 has affected some of our earlier planning. So hopefully, when things get back to normal, we can plan or replan what we had earlier. Okay, so I just have a short presentation to make, just as introduction to Multimedia University. So if I may share my slides, okay, just it will take long. Hold on. I'll just share my screen. Okay, can you see the screen? The presentation slide?
Yes.
Yeah.
Okay.
Okay.
All right. So, so my name, I'm Fazli. I'm currently the Dean of Faculty of Engineering and Technology. I'm coming from Multimedia University in Malaysia, and there are 3 campuses. And MMU is called MMU in short, and is the first private university in Malaysia. Was established back in 1997. And it's a subsidiary of Telecom Malaysia, major telecoms company in Malaysia, and it was established in conjunction with the formation of the Multimedia Super Corridor back in 1997. And to date, we already have 3 campuses. We have one campus in Cyberjaya, which is the main campus. which is about 45 minutes from the capital city, Kuala Lumpur. And then Malacca campus, I am situated in the faculty I'm working with currently, Faculty of Engineering Technology. And the same for Prof. Gu Bunchat is in Malacca campus, about 1.5 hours from the Cyberjaya campus down south, on the way to Singapore, the way to Johor. And then we have Johor campus, which is housing one faculty, Faculty of Cinematic Arts. And currently we have about 12,000 plus students, 5,000 students in Cyberjaya, approximately 7,000 students in Malacca campus, and another 120 students in Johor campus. Okay, so in terms of international students, we currently have around 1,000 students from 64 countries, and Indonesia is one of them. Indonesia forms 6% roughly of our international students composition, and most of our international students come from Bangladesh, 18%. We have from Yemen, 13%, Egypt, 9%, Saudi Arabia, 8%, Indonesia, 6%, and so on. Okay, so most of the students, international students, are in Cyberjaya campus, about 76% of them. Okay, maybe because of the lifestyle in Cyberjaya is a bit different from Malacca. Malacca is more of a historical city. Cyberjaya is the modern city, so they have different environment. Okay, so we have 10 faculties. We have programs and research in engineering. We have people working on IT, computer science. Okay, we have the faculties focusing on accountancy, business management, and we also have a law faculty in the university. We have a faculty focusing on communication. And we also have those focusing on creative arts, okay, such as creative multimedia and cinematic arts. Okay, so these are the spectrum of areas or fields which we offer at the faculty as far as undergraduate programs and as well as research programs. Okay, and these are some of our notable graduates. So to date, we have already produced 63,000 graduates from 2002, and some of our alumni have been successful entrepreneurs. Okay, whether it's in engineering field or in creative multimedia, cinematic arts. Okay, so we also have some successful film directors, animation films. If you're aware, if you are familiar with Upi Ipin or Bobo Boy, okay, so some of them are some of the entrepreneurs actually graduated from MMU. Okay, so let me just show you some brief video about some of our facilities, just to give you an idea of what facilities we have at the university. Okay, so this particular one is in Malacca campus in my faculty. Okay, so basically the facilities are meant to give or to prepare students with conducive learning environment and not the traditional learning environment. And it's also available at the Faculty of Business, this particular lab known as IB's lab. Okay, so this is one of the industry-funded lab known as Astro Lab at the Faculty of Creative Multimedia, the Cyberjaya campus. They do a lot of animation, digital creation. So this is in our other Faculty of Engineering in Cyberjaya campus. Okay, so they also offer some programs which are focusing on electronics program in telecommunications, nanotechnology, as well as electrical engineering. Okay, and there are also facilities to encourage entrepreneurship, spaces where students can assemble and discuss ideas and have pitching presentations. Again, here, this is our 24 hours learning point. Okay, so it's open 24 hours. And this is one of the labs situated inside Berjaya campus with the Faculty of Computing and Informatics. So they have this interactive table. And here we have space in the Faculty of Management. Known as the Siri Lab. Okay, some of the facilities in Faculty of Information Science and Technology. So over there, they offer IT programs and also bioinformatics program. Okay, and finally, this is the e-moot court for the law students. Okay, law program is also quite popular program in MMU. Okay, and besides that, of course, we have all the other basic facilities, such as recreational facilities such as a swimming pool and then 3D cinema, stadium, gymnasium, so on and so forth. And when it comes to research, on top of the various research fields, okay, so at the Faculty of Engineering and Technology, Prof. Koo will be giving his lecture on remote sensing and radar technology, okay, working with one of our which is our Deputy Dean in charge of Research and Innovation, Dr. Chan, has a lot of projects related to remote sensing. So later on, he'll be delivering a lecture on his work with the Center for Remote Sensing and Surveillance Technology. Okay, and besides that, we also have a close relationship with the industry. In particular, we have a collaboration with ZTE, telecommunications company from China. Okay, they have they have a training center in the Malacca campus to focus on 5G research and technology. And we also have other funded projects, other funded labs and spaces with the industry. Okay, so these are just some of the industry we are closely working with. Okay, they are private companies as well as government-linked bodies. Okay, so in terms of some recent research, in the news, I think you have heard about the first image of the supermassive black hole, and that was successfully captured. And one of MMU's alumni, Dr. Kevin Hui, from Faculty of Engineering, was one of the team that actually successfully came up with that first image of the black hole. Okay, and of course there are some, as I mentioned just now, some entrepreneurs who have been working on animated series and movies, animation movies, Bobo Boy and of course Upi Ipin and Agent Ali and so on. All right, so those are just some of the snapshots of the university. So do connect with us. Okay, we have our website as well as Facebook, Twitter, Instagram, and YouTube channels that you can visit. Okay, so thank you very much.
Okay. Thank you, Dr.
Thank
Patrick.
you very much.
Okay, welcome.
Okay, we'll go to the next agenda, which are our main agenda, the lecturing session by Professor Dr. Ku Fonchet with the theme Remote Sensing with Imaging Radar. The presentation will be moderated by Dr. Kurnia Ningsih. But before we start it, I would like to remind everyone to mute their audio. And if you have any questions during the presentation, please write it on the chat box, and then we'll let you ask it during the Q&A session. Okay, we'll go straight back to the next agenda.
Okay, thank you, Mbak Ani. Okay, hello everyone. I'm Kurnia Ningsih. I will be the moderator for today's lecture. But now first, I'm going to introduce Professor Ku. May I share screen?
Oh, sorry.
Yeah, actually, it's okay, fine. So today's lecture topics is about remote sensing with imaging radar. We welcome to the speaker, Professor Insinyur Dr. Ku Fonchet. He is a full professor at Multimedia University, MMU, Malaysia. He is also currently chairperson at the Center for Remote Sensing and Surveillance Technologies at MMU. He is also currently vice chair at IEEE Geoscience and Remote Sensing Society Chapter Malaysia sections. His research interests are remote sensing technologies, signal processing, data analytics, and embedded system design. He is a registered professional engineer and also a fellow of the Asian Academy of Engineering and Technology. He is also founder of a spin-off company from the University Research Center. So this company, iRadar, was incorporated in 2011 with primary focus to provide smart sensing and AI solutions for Industry Revolution 4.0, precision farming, and more. We also would like to welcome to all participants who are joining us today, both through Zoom and also YouTube channels. So to all participants, you can write your comment and questions through chat box in this Zoom or YouTube channels. Currently, more than 350 participants already registered in this today's guest lecture. Okay, now it's time for Professor Ku to deliver a talk. Professor Ku, time is yours.
Thank you, Dr. Nia. Selamat siang to all, especially to Pak Budi, to my Dean, Dr. Fazli, Dr. Nia, and all our colleagues in Polytechnic Negeri Semarang. I'm also very honored to be invited to give a lecture today. So as mentioned, I'm a professor in this Faculty of Engineering and Technology in Multimedia University. Just to let you take a look, my campus, this is my campus in Malacca. So not sure if you have visited Malacca before. Well, maybe this time is not a good time to visit, but I hope later if we have a better condition, you can come to visit Malaysia and also Malacca. Okay. Here I play a short video on our campus. This is Malacca campus, and I'm in this the Faculty of Engineering. Okay. Oh, sorry, a bit technical error in the video. Okay, let me skip this one. So basically, in our campus, we have a few engineering programs. One is called the telecommunication program, electronics engineering, major in telecommunication. The other is majoring in robotics and automation. We also have a mechanical program. Okay? And I'm now attached to this robotics program. And we have a research center called Remote Sensing and Surveillance Technology. Okay. So today, I would like to share with all of you some key point. Okay, in my lecture, I'm going to cover these three main parts. The first one is just to share with you what is remote sensing, okay, in general, and then why we have to pursue this remote sensing. The second is actually on the overview of the imaging radar, okay, the theme or the topic that I'm going to cover today, which is on the imaging radar. Or in more technical term is called a synthetic aperture radar. And then I would also like to share with you some of the application of this remote sensing in Malaysia, particularly in environmental monitoring. Okay, so as mentioned by Dr. Nia, if you have any question, just write down. I try my best to answer later on. Okay, so let's start. So this is an image of the Earth in 1972, okay, taken by Apollo 17. At that time, actually, when we talk about remote sensing, mostly it is using the optical camera. Remote sensing, what does that mean by remote sensing? Okay? Remote sensing basically is a long distance or contactless kind of information data acquisition, okay, without physical contact with the object under observation. Okay, like for example, our eye is a sensor. Okay, our eye is receiving optical wavelength, and this our eye is actually a passive. We call it as a passive sensor because we do not transmit any signal out. A camera, a normal camera, our digital camera, or the camera from your handphone is also a form of optical sensor, whereby you can actually through this sensor you can look or look at the world or others images. Okay, so remote sensing here we can say is an acquisition of information about an object or phenomena without making physical contact with the object. Okay? So here the key point is without making physical contact. So there are different type of sensor, like for example, say touch switch. For example, all these the sensor, capacitive sensor, inductive sensor, where you may need to have a contact between the object and the sensor. So that is different category of sensor. But when say now we want to look at our Earth, for example, at outer space. So the only thing we can do is actually through some sensor which actually can make or acquire the information at a far distance without physical contact. Okay, so based on the sensor, there are many information we can actually gather. Okay, one example is that say we look at our Borneo island. So at the 1915s, you can see based on the image. Okay, this is actually optical image. Based on optical image, you can see almost the whole area is actually covered by forest, a vegetation, very dense vegetation. And from years to years goes by, then you will see they are kind of getting less and less green area. And this green area, if we can correlate, is actually related to the forest, and from here we can actually understand that there are some serious deforestation activity going on. So from the remote sensing, we can actually try to understand the current condition or situation of our Earth. Okay, example here is say the flood. Okay, we can monitor flood by using satellite-borne remote sensing sensor. We can also try to monitor the severity of the floods and also deforestation through remote sensing. And of course, this is after the disaster or after the things happen. Currently, what we are going to use also is we use a remote sensing techniques to do prediction. That means before the things happen, we try to do a prediction when the things may potentially happen. So this we can use for early warning and detection. And if you can look at the whole world, today we have this COVID-19 issue. But other than this, actually, we also have others issues. Okay, like for example, the some of these like just now we mentioned the deforestation. Okay, we have environmental issue, global warming issue, tsunamis. Okay, earthquake, natural kind of disaster, as well as other type of made or due to the human activity. We have some of the contamination or pollution issues, and all these is actually are going to impact our future. So and how we can actually solve this thing is really we have to work together globally across all countries. Okay, so one thing I would like to say is that we do not inherit the earth from our ancestor. We actually borrow it from our children. Okay, so we should preserve our earth, the environment, and so on. And one way to do this is actually through remote sensing. We need effective remote sensing tools to provide consistent, timely, and large-scale measurement of our environments. Currently, what we have is actually there are many technologies and also many tools that we have developed worldwide with many other countries, from the ground-based system to a low altitude airborne system, to a higher altitude airborne, and also to the spaceborne. So we need different types of sensors to continue monitor the quality of our Earth, and from there we will know what are the actions and also some issues that we have to take action at what time. Okay, example. So this is something like say we as our as a human, we want to do a body checkup every year. Okay, so we have to go to hospital, and then we get our blood test, do X-ray scanning, and so on, just to understand whether we are healthy or not. So our Mother Earth, we also need to do body checkup, but this time is actually we use different tools or different technologies to help to do the monitoring. We can only take action if we know what is going on. So like for example, say air quality. So sometimes we have a pollution, air pollution. So we need to know where is the source and how serious, and all these things actually we can use a kind of sensors to do the monitoring. And based on all this, then we can try to plan out what will be the follow-up action we need to take in order to prevent or also to minimize the impact. So in terms of the remote sensing technology, we can actually classify or try to divide into few areas. Okay, so when we talk about remote sensing, then the thing of course is we need a sensor. Okay, so there are many researchers or the scientists that work on sensor development. Okay, so that means it's to design and to develop sensors. And after we make the sensor, then we need another team to do calibration. Okay, because in order for the sensor to be useful, then we have to make sure it is actually well calibrated, the data is accurate, consistent, and also is useful. Okay, so that is actually another group. And then how to deploy the sensor. So after you get the sensor, you have to say deploy onto a spacecraft, satellite, or you want to deploy onto a drone, or just put as an IoT station on the ground. So this is on the deployment. And then all this when set up, then we will do the data acquisition or the image acquisition. So it depends on what are the sensors we are dealing with. Some sensor will give us two-dimensional image. Some actually will be single dimension, or some is actually multiple dimension. Okay, so the first part of the remote sensing technology is involving the sensor design and development. The second part of the remote sensing technology is actually involving a processing. So it is like signal processing, image processing, classification. Now is a lot of AI. You use the AI to do the classification and detection. And also, in a way, all this has to correlate with the theoretical modeling and also experimental results to do the validation and so on. So this is on the processing of the remote sensing signal and images. Then the third part of the remote sensing area is actually on the application. So once we get the sensor, we do a good calibration, and then we get the data and the information. Then the last step is actually how are we going to use it and to apply to what area. Okay. Here I just listed down some of the potential area like land use, paddy yield prediction, oil palm growth monitoring, disaster monitoring, terrain mapping, coastline monitoring, and so on. So all these are the application of remote sensing that currently we have. In terms of the sensor, okay, in terms of sensor, here is actually a diagram showing different types of sensor that we can use in remote sensing. Okay, just now I mentioned our eye is actually a sensor also, but our eye is called a passive sensor. So this passive sensor means there is no transmitter. Okay, there are another group of sensor is we call as an active sensor. So active sensor means there's a transmitter. So like for example, a radar system is an active sensor because radar system, it will transmit a signal, a radar signal, and this radar signal, it will hit to a target, and then there's another receiver that we can receive the reflection or the reflected signals. Okay, so that is called the active sensor. A laser also is active. Laser, if you look at all those laser sensor or LiDAR, they actually will send out a laser wave to the target. Okay, so you can see it's a red line, very clear and very sharp. Okay, for passive sensor group, normally we understand is the camera. Okay, so all those are optical camera. This is called passive, and where it gets the information or the image is actually through sunlight. So our sun is actually considered as the transmitter. It will emit all the lights, the source, and then from this light, a portion of it is actually reflect and hit to the camera sensor. So the camera is actually sensitive to some of these microwave, this optical wavelength. So from there, they will form the image. So these are the two groups. And of course, the passive group will be relatively easier because you do not have transmitter, you only have receiver. So about 50% less work to be done. For active group, there will be more complex because you need to carry your own sensor, own transmitter. So the good thing about active sensor is that when we have active sensor, basically you can operate the sensor day and night, regardless of the weather condition. Normally for passive group, like for example, your camera, we can only operate when it is a good weather condition. Like for example, daytime, we can see all the image very clear because there's a sunlight. But at night, nighttime, it will be blur because there's no sunlight. So it is actually dependent on the weather condition. Raining, you may not be able to see, and so on. Or cloudy area, you also cannot see. So for active sensor, that do not have this issue because for active sensor, we can select a proper wavelength to see through or penetrate through, say, cloud or through the dark area. So that is an advantage of the active sensor. So now the synthetic aperture radar is actually grouped under the active remote sensing sensor. In short, we call as a SAR. Okay, so this SAR in radar term is referred to synthetic aperture radar. Okay, so synthetic aperture radar is one type of radar system. It is a coherent side-looking radar system, which is capable of producing high-resolution image. Okay, so this is the definition that we can say. Here summarize the all the key points of synthetic aperture radar. Okay, so first we call it as a side-looking radar. Okay, side-looking radar means the radar is looking at the side, not at the front. Okay, like for example, say our eye we look to the front. Say this whether it's front or side, it depends on the path of propagation or your walking path. Say if as a human we walk straight, okay, our eye is actually looking in front. Just imagine that this radar, if you walk straight, your head is actually moving and look at the side. So that is called the side looking. So radar, when you travel at the certain path, and then the sensor is looking at the side, and then it is coherent. Coherent here means this is a phase that have a steady phase, and from one capture to another capture, the phase stability is maintained the same. Okay, so like for example, you start send a signal with a 0 phase. The second pulse when you send is also a same 0 phase. So coherent radar, and also is a side-looking radar, and because of these features, they can produce a very high resolution image. So this SAR radar is actually is an imaging radar, meaning it can produce image. There are also some radar, but it cannot produce an image. Okay, so this is a different category. So normally when we talk about SAR, first I will want to also introduce to you the inventor of the SAR, which is Carl Wiley. He's actually filed a patent in 1965. The method at that time it called the pulse Doppler radar method. Okay, so it's a bit similar to the Doppler radar, but actually it's more complicated. And based on that pattern and also the idea, then there are many scientists and engineers that produce different types of variant of the radar according to this idea. Okay, before I go into more details on the theory or concept, let me show you some of the results first. Okay, so this one, for example, it is the mountain Mayon. This mountain on the top is actually Google Earth optical image. Normally, if you use a Google map, you can see there are a lot of white spot. So all this is actually the cloud. Okay, because say now the satellite is actually flying at a very high altitude, and then the camera is actually looking down, and then of course there are crowd. Okay, there are crowd at especially in our area. Okay, in Malaysia, Indonesia, and this part of the world, always is very crowded. So a lot of time you cannot really see a very clear image of our Earth. Okay, it's blocked by the crowd, and this camera cannot see through because it's optical. The wavelength is very short. And on the bottom part, this is actually the current state of the art image captured by a radar, a synthetic aperture radar. So you can see it's actually very sharp, very high resolution, and you can see also the kind of a 3D effect. So this is what we can do now by using a radar, and there's no crowd. Okay, the crowd is actually we can see through. Okay. This is another example. This is another mountain. Okay, is actually a active volcano. If you use a Google Earth again, we can see quite a poor resolution. But if we use a very high resolution polarimetric SAR, you can see a lot of clearer, very good signature. Okay. So when we talk about radar system or remote sensing in general, then there are things that we need to understand what we call as a electromagnetic spectrum. I suppose for some of you, if you are studying engineering, and especially if you are studying electronics or electrical engineering, you should study about what is EM, right? The electromagnetic wave. So when we talk about this, it is actually similar to the light. The light is actually one area or one spectrum of the whole electromagnetic spectrum. Our visible light, it is somewhere around here, where the wavelength is actually in the order of 10 minus 6 meter. Okay, and then the frequency is about 10 to power of 14 to 15 hertz. So this is our optical wavelength. Okay, our visible light. So the wavelength is actually very small, in the order of a micrometer. And then microwave is here. So like your microwave oven, okay, the frequency, the operating frequency is actually lower than the visible light, but then the wavelength is actually longer. Okay, so the wavelength is in the order of millimeter to this 0.1 to 0.01 meter. So this microwave is in the area of centimeter wavelength, and this centimeter wavelength is good enough to see through a water droplet. So therefore, you can actually see through the cloud. And radar system, typically we operate at this frequency. Okay, so it's in terms of a 10 power of 9 to about 10 power of 10 and so on. So normally 10 power of 9 we call as a gigahertz. In the telecommunication actually is also in this area. Like for example, now we have our smartphone. Normally we say it's 2.4 G, okay, 2.4 gigahertz, and 2.4 gigahertz is around this area. Okay, is around the L band to P, L band to close to C band. So that is actually the operating frequency of the telecommunication device. But then for radar device is slightly higher, okay, where the frequency is higher and therefore the wavelength is actually longer. And in order to receive a signal, normally we need to use the receiver is called an antenna. Okay, the transmitter and the receiver are all antenna. So why we use microwave instead of use the visible wave is because of the behavior of this EM wave in response to the atmospheric condition. If you look at this one, is actually the absorption band. If say this is a visible light, okay, visible light, you have a very high absorption. Okay, absorption here means if say I pass through this atmosphere, and the atmosphere, if it is a visible light, most likely the energy will be absorbed by the atmospheric areas, like and also the cloud, and therefore when you hit to the ground, it will be very less energy. But if you look at microwave, the absorption band is actually very low. That means there has very less attenuation in this region, and therefore it will be very ideal and good when we transmit the signal at this region. There's less energy get absorbed and absorbed, then therefore you get a very good signal return. Okay, so or in short, what I'm trying to say is because of the characteristic of this or the nature of the EM spectrum, the radar system which operate at microwave frequency typically can operate under all weather conditions. Okay, here I want to show you a working principle of a SAR system. So this is, imagine this is an aircraft. So aircraft want to travel in this direction, and then there's an antenna that look at the side. Okay, this is a side looking, and then when it moves, okay, it travels. So the antenna also travel together. So when this antenna travel, so it will capture from one point to another point. It captures the signal. So for at every point, the antenna will send a pulse and then hit the area, and then there are certain part of the signal will be reflected back to the antenna. So based on this, we capture and then we process the data. So this is one capture. Then after that, when the airplane move, then you capture another time, and then you capture again. So after multiple time of capturing, you can actually form an image. Every capture is just, you imagine, is a line scanner. Okay, one capture is one line. So you have multiple lines, and then based on that, you combine together, then we can form an image. So the motion of the antenna is used to synthesize a very long antenna. Okay, so if you happen to study this antenna theory, so there's the underlying principle saying that if your antenna is short, very short, then you have your resolution is very gross. If you want to have a very good resolution, you need to have a very long antenna. But then if you want to have a very long antenna, it's not feasible if you want to carry on board aircraft, because there's a limit for the aircraft to carry. So in order for us to get a very long antenna, this is what we do. We use a motion of the antenna, okay, to synthesize a very long antenna. That means virtually there's a very long antenna, but physically actually is a very small one, a short antenna. This is an antenna, the physical length. But then because this antenna travel from here to here, so we will think, or virtually by using signal processing, we can have very long antenna. Okay, so based on this concept, we get a very high resolution radar system. So over here, I want to show you some of these satellite-borne SAR system. Actually, there are already a lot launched to the space. Okay, the old one in 1980s up to now there are a lot of commercial synthetic aperture radar system, which is actually fully operational, and also we can actually get the data from through online order and so on. Okay, there are also some SAR system actually mounted on airborne from a pressurized aircraft operating at a very high altitude. So all these aircraft typically they operate at 10 kilometer and above the sea level. Then also nowadays, because of the advancement of the technology, we slowly bring down the synthetic aperture radar system to a smaller size, and currently there are a lot of activities in progress to mount the SAR system onto a drone. So a drone, as we know now, not most of the time the drone they carry only the camera, optical camera, which is actually very small camera. But then now for the SAR system, slowly they will also have some small SAR system coming out, which you can mount onto the drone for more real-time application. All right. So in terms of the SAR image, normally we say in radar image, the highest resolution radar is called a SAR. So how we calculate the resolution? We can say there's a two dimension. There one is X dimension, the other is a Y direction. Okay, X direction is actually a cross track. Okay, so this, if the aircraft they fly in this direction, across the flight path is called the X direction. or the across track direction, and then along the flight path is called the along track direction. So so the high resolution is obtained by using special techniques. For range or the X direction is called we use a pulse compression technique. And then for the azimuth direction, you use a synthesized long antenna technique. Okay, so actually there are two technology here to form a good resolution image. One of the technique, this technique is actually used in all the radar system, not only SAR system. Most of the high resolution radar system, they use a technique called pulse compression technique, whereby, say for example, you have a very long pulse. After, by using a mesh filter, you can actually reconstruct a very sharp pulse. Okay, we need a very sharp pulse is because when this is very sharp, then you can actually separate or differentiate from pulse to pulse at a very close distance. So the resolution will be better. But if your pulse is actually very wide, then you may not be able to separate between two very closely located targets. Okay, but then if you send a very short pulse, the issue is the energy is actually not enough for the signal to send and then to receive back. Imagine that now we are talking about we want to send a signal at a very far distance, like for example 10 kilometers. So we want to send a signal and then we want to receive back the signal. So the energy has to be sufficient for the signal to travel along this long distance. So we need sufficient energy. At the same time, we want the pulse to be very short. So if we do not use pulse compression technique, it is actually very hard to achieve. But luckily, there's a technique that can be used. The other dimension is actually we call it the azimuth or the along track dimension. This one is if you remember just now when we talk about the antenna, when we move along, okay, then we can actually form the image. So from every line. So imagine this is every line. Every line is actually constructed by moving to another location of the platform. So after you move, say from -4 0.4 meter to say positive 0.4 meter, then you construct this image. But then here you can see because of the antenna behavior, the bin of the antenna is actually there's a cone shape. Okay, so it won't have a very good resolution. You will see the target, okay, spread over the antenna or the azimuth direction. But luckily, there's a technique which is what we call as a synthetic aperture or azimuth compression technique. Okay, where you can actually do through image processing or signal processing, we can reconstruct this one, and then we get a very focused target image. Okay, so this is actually along the azimuth or the along track direction. Okay, so for the normal radar system, this is the resolution. Okay, but for synthetic aperture radar, the resolution is actually D. D is actually the antenna physical length divided by 2. So just to show you one example, say we have a 10-meter antenna, 10-meter length. Okay, the length of the antenna is 10 meter long, and then operating at a 800 kilometer range. Okay, at a very far distance, 800 kilometer. This is a space, okay, at the space altitude. Then the lambda of the wavelength of the radar is 25 cm. So based on this calculation, if we use a normal radar system, the resolution is 20 kilometer. This was before we have this new SAR design. Okay, but if you use the SAR system, the techniques that I explained just now, we can go down to say 5-meter resolution. So it's actually a very big difference by using a synthetic aperture radar technique. So this is actually another advantage of SAR. The SAR resolution is independent of sensing distance. So like for example, optical camera, if you know how to say if you are very interested in photography, you should know the resolution of the pixel resolution of your camera image is actually dependent on the sensing distance. You go further, then of course your resolution wouldn't be good. Okay, you need to do say a zoom in, okay, using optical lens. For this radar system, the advantage of why now for most of the satellite borne high resolution image is all will be taken by SAR is because they are independent on the sensing distance. So regardless of how far you go, as long as you get enough energy to transmit, you can get a same resolution. Okay, 1 km or 100 km is the same. So so this is another picture of the SAR image. Nowadays, a SAR image can be actually very high resolution, up to sub-meter, okay, sub-meter resolution from the sky. So what does this SAR or the radar measure? Basically, there are two parameters. One is called the power, one is a phase. Okay, so if you study electromagnetic spectrum or the signal, propagation of a signal, or you can use an oscilloscope to know if you can measure the signal. Normally, you see there's a sinusoidal wave. Okay, so EM wave typically you can model as a sinusoidal wave, and from the sinusoidal wave, if you look carefully, actually what we receive or what we measure is actually there are only two things. One is the power. This power is like your voltage square, okay, voltage times 2, no, voltage times voltage, okay, so it's a voltage square is called the power received. The other is a phase. The phase is actually the sinusoidal. When you look at the sinusoidal, it tells you when this sinusoidal wave start to transmit. So the relative phase is also another very important parameter to measure. Normally, for most of the radar system, they just measure power. They don't have a phase information. So if you don't have a phase information, you cannot do the coherent summation. Okay. So for this particular slide, I just want to show you one of the very important equation. This equation is called a radar equation. Normally, if say you want to design radar, you want to develop radar, or you want to study radar, then you have to study this equation. Okay, looks complicated, but actually not. Okay, let me just briefly explain. Okay, I don't want to bore you on this one. So P here it refer to the transmit power. G here refer to the antenna gain. So basically, what it means is that, for example, say you have a antenna. This antenna is a transmit antenna. Then you have another antenna is a receive antenna. So the power equation is actually it tells you from the transmit power after I pass through antenna, then I will need to pass through a space. This space there's a propagation attenuation. The attenuation is actually in this form because of the wave propagation. The attenuation is in the order of a spherical attenuation. Okay, 1/4 pi r square is the resultant of the spherical propagation. Okay, then you hit a target. For example, this is a target. Then after you hit the target signature is called sigma. Okay, and this is actually what we call as a radar cross section. Okay, this is the one that we want to measure, is the target parameters. Okay, then after that, after hit the target, some part of this signal is going to send back to the receiver, and then of course it will go through another attenuation. Then after that, it will be received by the receiver. So when you receive by receiver, you have to also multiply the factor which is actually related to the efficiency of your antenna. So based on that one, then you get a receive power. Okay, so from this PR, this is a receive power. So the power received here is a portion of the power transmit, and also multiply all the factor related to the interaction between the targets and the atmosphere. Okay, and based on that one, we come up with a term called radar cross section. Okay, so radar cross section is this term, the sigma term. Okay, and if you look at another thing I want to highlight also is, if you look at all these terms, sigma is the one that related to the target. That means this is the thing that we want to find. The rest of the thing we can control. Power transmit we can control by using your signal generator. The antenna gain you can control by designing your antenna. The range you can set, or you know the range when you know where you want to measure. Okay, so all other things is actually controlled. The wavelength also we control because we generate the signal, and then the power received is actually what we measure. Okay, so based on the power received, what we want is actually to recover the sigma, and based on the sigma, actually we can tell a lot of things. Like for example, say based on the regular cross section, we want to understand whether the target is a spaceship, is a airplane, is a bicycle, or a car, or a human. Okay, because for different target you have different reflection, and so that is about the radar cross section. Okay, then based on all this basic concept, people start to build a radar system. Before I show you some of this interesting radar hardware, I want to share with you two techniques that we use in SAR. One is called interferometric SAR, the other is called polarimetric SAR. These are the two very important concept and also configuration in SAR. So interferometric, it means a phase difference, okay, or interferogram. Okay, so this is an interferogram or interference image. So in radar system also, the behavior is very similar to, like for example, if you look at the water or the sea wave. Okay, it's just that the EM wave we cannot see by using our eye, because our eye is actually limited to optical wavelength, and optical wavelength is so small that our eye cannot have a good resolution to detect the interference. But if we use a microwave, actually based on the microwave return, and if say you have two antenna or two system, and each of them they have a different antenna which is actually located at a slightly different location. When you look at the same area, then based on the construction of the wave, you can see a interference or the interferometric signature. So what is the use of this is that based on the calculation of the phase difference or the phase shift, we can actually recover the height information. So this is actually a very important discovery, whereby by using an interferogram or the phase difference, we can actually know the height of a target. Okay. Just now when we talk about the radar, imaging radar, we are saying that the radar have two dimensions. So it's basically we have two-dimension image. But when we have this interferometric techniques, we actually can build a three-dimensional image. Okay, this is one of the example of SAR image. You can look at this one. It is a 3D image. But imagine that this is actually one capture by using, say, an airborne system. Okay, we fly through the path one time, but the platform actually carry two antenna. So one antenna will give you one image, the other antenna will give you slightly displaced image, and both of them they combine together by using interferometric. We can form a 3D image of the area of interest. Okay, so this is actually far more powerful than any other techniques. Another application of this technique is actually to do temporal change detection. So like for example, say earthquake, when we have earthquake before and after earthquake, then there's a slight displacement of the terrain. So when we use the same radar to capture before and after the earthquake happened, then we actually can see all the fringes, and all these fringes will give you the magnitude and also some calculation on what is the movement of the earth, and also where is the source of the movement. Another techniques that I want to share with you is actually what we call as a polarimetric SAR. So polarimetric SAR, it measures the scattering property of the object. Okay, so this one is a bit more abstract. I will not go into details, but generally, what it means is that for the wave that the wave that transmit out the radar signal, if we can imagine, like for example, from the oscilloscope, you say just a sinusoidal wave, right? But this sinusoidal wave, what we see is actually one dimension. But imagine that in the free space is actually the wave propagate at 3 dimension. So they always have an orthogonal set. That means if say your wave, one dimension of the travel is actually at say the vertical direction, then the other wave is actually carried at the horizontal direction. So based on this property, actually we can build a matrix. We call it a scattering matrix, where you can describe the different direction of the wave propagation. And based on that, if we further decompose the scattering mechanism, we can actually try to understand the properties of the scattering. Okay, but to do that one, we need 2 set of antenna. One set of antenna pointing at the say horizontal or vertical. The other set you point at the horizontal direction. So you receive the signal at vertical as well as you receive at the horizontal. So based on that, we can actually calculate what we call as a surface scattering component, a double bounce component, and volume scattering component. Okay, when we can do that, okay, what happens is that we can do a lot of very good classification on the area under observation. Okay, like for example, say the city area, because city they have a lot of buildings. When you have a lot of buildings, the main reflection is actually from what we call as a double bounce reflection. So this reflection, it gives you the strongest energy when you have a very good, say a building or a reflector. Okay, so those very strong reflection from the buildings will give you information on this is actually a city area. Those are vegetation area. Normally, they will give you a very strong return from the volume scattering because of the random nature of the vegetation. So based on that, we can actually do an analysis of what is the percentage of area that is actually covered by city, what the area is actually the terrain area, or some area is actually is a water or the flooded area, and so on. So from that analysis, you can actually extract a lot of very useful information. For example, we can use this one to detect earthquake, seaquake, tsunami phenomena. And for this particular diagram, okay, this is also an image of a polarimetric and interferometric combined together, where you can see the Eiffel Tower. Okay, give you a very 3D kind of a view, and also we can identify this is actually a building at a different height, and then that can give you a very precise calculation of the distance and also the altitude. Okay, so this is actually another thing as compared to optical sensing, radar sensing. We can actually do a measurement in terms of the all these parameters. Okay, the height of the building, for example, we can do the measurement, and also whether the building or whether the target is actually a metal related, or whether it is actually a vegetation, and so on. This is another.
Prof. Go, I'm sorry. I think we couldn't hear your voice. Is there something wrong? No.
Hello, can you hear?
Yes. Yeah, now we can hear your voice. Okay.
Oh, sorry. Okay. Should I repeat which part you lost my voice?
I think 3 slide previous.
Oh, this one?
Yeah.
Okay. The last thing I want to cover is actually I want to show you some of the application we have done in Malaysia. Okay. Just a bit of introduction of my center. Our center is called Center for Remote Sensing and Surveillance Technology. We started in year 1997, okay, where we formed our remote sensing group, and from that point onwards, we actually built different types of sensors. We focus on remote microwave sensor development. Here, I'm going to show you some of these the sensors that we built. Okay. So before actually we build sensor, actually what we do, we study on some of these the theoretical model of the radar cross section. For example, say in Malaysia, we have a lot of vegetation and also a forest. So the dense forest, we model by using cylinder and ellipsoid, to understand if say I have a microwave signal, when I send a signal to this vegetation or the canopy, what will be the interaction, and then how strong is the reflection to my radar system. So to verify and validate our theory, we actually built an anechoic chamber. So anechoic chamber is actually a room that is actually very quiet. Okay, it quiets in the sense that it will absorb all the microwave signal. So this is all the absorber that we built in Multimedia University, where we use an antenna to transmit signal to a target, and then we want to understand the reflection. Then we built one thing we built is actually we call it a scatterometer. If you can see here, there's a polarimetric antenna. There's an antenna here. We mount the antenna and also the sensor on the tip of the boom truck. This is the boom truck. So we extend the boom to a very high. This is about 20 meter high, and after that we use a radar to look at the paddy field. Okay, this is a paddy field, and then based on that measurement, we want to correlate to the growth, paddy growth, different stages of the paddy growth. The paddy actually behave differently, and then the response from that to the radar is actually different. So we do paddy field monitoring, the oil palm monitoring by using this technique. Then we also correlate the study with some satellite-borne SAR images. And after we make all these scatterometer, the next thing is we start to build our own sensor, okay, the radio frequency component. So this was one of our early prototype. Okay, all the microwave components, the delay line, the intermediate frequency, the circuits, and also the transmitter, and also the mixer. So we use a system to do the measurement together with our agency of remote sensing. And then after that, we started to build a more complex system where we need to have a track for the sensor to move. Okay, remember just now I mentioned for synthetic aperture radar to be used, we need a movement of the platform. So we built a track at this the boom truck, and then we try to move the antenna. So when we move the antenna, we will capture the signal, and from there we do further image processing. Later, we built more complex system. This is actually the antenna that we built. Is a microstrip antenna, and the design actually we want to mount onto the UAV. Okay, because eventually we want to make the system to be on board a airplane. So to do that, this is actually one of the prototype we have. We have the whole the radar system with electronics component, the radio frequency component, the data acquisition, onboard computer, everything in one box. Then we mount onto airplane. Okay. So this is actually some of the design we have from the FPGA to the others controller and processor board, and also different types of antenna design. And we mount onto one of our UAV. This is actually an unmanned aerial vehicle. This UAV is actually designed in Malaysia. Okay, and the antenna actually we just mount at the bottom of this UAV. So this is actually one of the flight mission we have in Malaysia. So this is a UAV, and then what you see here is actually the antenna. So when it flies, this antenna is actually a beam steering antenna. It will look at the side. Okay, say if the flight path is this direction, then it will look at the side. Over here, you can see here, this is actually one of the image that we obtained by using that UAV SAR system. Is actually this is a map of the river. Okay, the return is actually at the C-band. C-band is at 6 gigahertz, which is actually a frequency higher than the current telecommunication band. And this is another picture of the SAR image. Okay. The other thing we have done after we have successfully produced the SAR system UAV base, we also try to look at other application of the SAR. Okay. One of the particular application we call as a ground-based temperature radar. This is one of the product that we produce and commercialize through our spin-off company. This system is actually a ground-based imaging radar system. It's a SAR system, but it's actually a ground-based system. The use of this is actually to do landslide monitoring. The system actually, there's an antenna, and then the whole system is actually can move along one direction. Okay, when we move this direction, then we also continuously capture and form the image. So we use this one to predict whether there's any movement of the land. So one example is that we do a continuous monitoring of a area, a highland. We call as a Cameron Highland. This is one of the very nice and beautiful tourist attraction place near Ipoh, okay, another state, not in Malacca, another state. Okay, so there's a area where it's actually there are some potential landslide. So we use that to do a monitoring. We build a house, and then we put the radar inside the house, the housing area, and then we do monitoring. And this is actually the radar image. If you compare the radar image and the optical image, they are kind of very similar, but also, of course, from the view of the perspective of microwave, it is actually there are some other information that we can extract. For example, every pixel of this actually it tells us the property of the targets, the returns. Okay, it will tell us about the information related to the distance and also related to the movement. Say for example, if we just closely monitor one point, when there's a change, you can actually tell there's a change, okay, at a very far distance. So the measurement we have done is about 1.2 kilometers away. A slight change of, for example, 0.5 millimeter. Okay? A 0.5 millimeter change, then we actually can detect that kind of changes. So we use this one to monitor any potential movement of man-made structure and also natural terrain. Currently, what we have is actually we make it to be more portable and more robust. So the system can actually put into a container, something like this, and then you can do a continuous monitoring of any area. Okay, this is another example. Say we have some targets. So when you do a long-term monitoring, if there's no displacement, then the graph is straight. Then if say there's a displacement, then you can see there's actually a movement, and that movement will correspond to the land movement. We can use the same techniques to do say a structural or the building monitoring. We can do a long-term monitoring of the building, the bridges, and if there's any changes, actually we can give a signal or alarm. Another application is actually on the LRT station. So for LRT or any bridges, sometimes we want to do an analysis of the how extensive or what is the magnitude of the vibration when there's a train passes through. So we can use sea temperature radar to measure the vibration. Okay, if you look at this one, the different color, it shows a different vibration when the terrain the train passes by. Okay, of course we can use this one for other application like to monitor the water dam, the volcano, and also others terrain. Here is another one of the latest image we obtained from one of our measurement with at Taipei city. This is actually one of the test site. The area is called a Kirong area. So we put our system at a distance of about 1.8 kilometer away, and this is actually the coastal line. So we want to monitor the coastal line and see whether there's any movement of the terrain. Okay, and this is another one that we monitor the fencing area, and then we want to see whether there's any potential displacement. Okay, so there are actually a lot of application of sea temperature radar for landslide and also structural health monitoring. There's another thing that we are working on is actually to put the SAR system onto a drone. Of course, currently, if you fly drones, or there are many drone companies, the payload is actually mostly optical camera. So what we want to do now is actually we want to put the SAR system onto the drone. But this is a bit challenging because the SAR system is more heavier than the normal camera. Typically, the SAR system, the one that we built now, is about 10 kilogram, and now we want to reduce it to about say 2 kilogram, so that you can mount the SAR system onto a drone. Okay, but at the same time, also we have a drone system that we use carry the optical image, optical camera to do different types of environmental monitoring application. Okay. Well, in short, I think imaging radar is one of the state of the art for today's remote sensing technology. In the past, when we talk about radar, normally we say radar, or we imagine the radar is for military use, or the radar is actually a very big antenna, okay, very bulky, and then not for commercial or not for civilian use. Yeah, that was like in the past 50, 60. Okay, but today there are a lot of application we use radar. Okay, even if you can if you are aware for a lot of new cars model now, they have radar. Okay, the radar is used for say to give you a warning when your car is closer to the front car. Okay, used for obstacle avoidance, used to sound alarm, and used to detect any potential collision. So radar now, it goes to a very small embedded form factor, and it is actually comes to the household. Okay, so radar, there are actually a lot of application. It is actually a complement technology as compared to the optical camera. Optical camera is good when we want to look at the signature, like because we have multi-color band. Radar, they give you a different information with regards to the property of the targets, the distance of the target, and also the phase information related to the target. So these are actually a different spectrum. So if we imagine our eye, we can have one eye looking at the optical images, and also the other eye we can look at the microwave images. So it is actually very powerful. You can, at the same time, you can look at the object, and then you can tell a lot of information like a distance, how far the target from you, and so on. Okay, so this imaging radar, slowly it will come to a very commercial application. Okay, and beside the radar system, actually, I would say for remote sensing, as far as the remote sensing is concerned, there are also various different type of sensor that can complement each other. We have radar on the one hand. There's also a LiDAR system, a laser system, can also do a very precise measurement on the distance. And also there are others like GNSS, GPS system, optical system, of course. So all these combined together, it will give us a very good information related to the, if we are talking about the environmental sensing. So complement of all this technology will give us a better understanding of our Earth. So in short, in summary, what I want to say is we need to jointly develop technology, okay, regardless of later what area you are dealing with. Okay, as far as this remote sensing technology is concerned, we need to share information, and we need to complement each other for the betterment of our nation and the environment. So there are many different types of sensors we have now. We don't have one single sensor can have all information. Okay, every sensor, they have strength and weaknesses. Every sensor also, they have some advantages and also some weaknesses. So each of them we need to combine. That's why now we are talking about data fusion. We are talking about AI. We are talking about the big data analysis. So it's about gathering all the information together to give us a holistic view or overview or more informative with regards to our environment. Okay, so with that, I thank you for your attention. So I pass back to you, Dr. Nia.
Okay, yes. Thank you very much, Professor Ku, for the great talk today. So we receive so many questions.
Is it?
Yes. Okay.
Shall I stop the sharing or pass back to you?
I will read the questions and
okay.
Then, yeah. First from Mr. Ronnie. So we had a project to find the ruins of the kingdom and reconstruct the shape of the city at that time. What remote sensing technology and method that fast, accurate, and cheap to answer the issue?
Can you repeat the question?
Okay, from Mr. Ronnie.
Okay.
We had a project to find the ruins of the kingdom and reconstruct the shape of the city at that time. What remote sensing technology, what kind of remote sensing technology and method that can deliver fast, accurate, and cheap to address some issues?
So that is actually a historical place, is it? What area is that? Is that a historical place?
I think yes. Mas Roni, are you there? Hello, Mas Roni. Mas Roni Apriantoro, are you there?
Yes, Miss.
Okay. Can you ask directly to Professor Ku explain?
Yes.
Can you turn on the video, please?
In our community, we had a project to find the ruins of the historical kingdom. So we technology
Is it
to
underground? Is it underground?
Sorry.
Underground? Is it underground?
Underground or
No,
in the forest? In a forest.
The object is not the underground, still in the upper the ground.
Okay. Is it covered by trees, covered by forests, therefore you cannot find, or what is the difficulties now for you to find?
Yes, the historical object is in the forest.
Oh, okay.
Oh, in the forest.
Okay. So if it's in the forest, actually there's another project very similar to what you described. I think it's in either it's Cambodia or in somewhere near the Angkor Wat or some area the other side. So actually they use satellite-borne SAR because if you just now when I mentioned about this SAR system, if you select a good frequency, you actually can see through the canopy of the forest. And if say you have these buildings, the building is hiding underneath the forest canopy. From the radar, actually it can highlight that building because the return it will have a different signature. But of course, say the area is actually very big area. For example, the whole Borneo Island is like a few hundreds or thousands of hectares of kilometers square. So it's also not so easy because it depends on how strong is the target return. They need a kind of quite a extensive processing to try to do a classification and to remove all those canopy so that you can find the building underneath. Normally, we select lower frequency radar. Say for example, P-band. L-band. L-band radar is actually very good for this kind of application. It will see through the forest because the forest canopy typically is about less than 1 meter or 1 to 2 meter kind of a thickness. Then the building is actually at the lower area, and then L-band is good to pass through the canopy and then find all the target, which is a man-made target. Man-made target will give you a very strong return. If you can, I will show you this one. Okay. So man-made target is actually very sensitive to PD. And for your application is like you need a parametric SAR operating at L-band. There are also some company that actually can do this. They operate the L-band airborne system, and they fly through the forest to look for all these the historical buildings and other things. The other thing is underground. There are also some building they hide underneath the ground level. So that one actually we use an even lower frequency. L-band you cannot see through. They go for P-band or even lower frequency UHF and so on. So it is possible that we use this imaging radar to help you to find the buildings.
Okay, thank you, Professor. I think it's not easy to imagine.
Well, if you want further information, maybe later we can talk offline on how to do that.
Okay, thank you.
Radar is not easy, yes. Radar is not easy, but it's doable now.
Yes, thank you. So another question is from Mas Saptaji and also myself, I think similar. So what are the potential and obstacles of remote sensing applications on human health, such as to detect the suspected of COVID-19 around the globe? And then what can be done to overcome the barriers to the use of remotely sensed data for human health purposes?
For human health detection, if you are talking about imaging radar may not be suitable for human health detection. Okay, but because radar we use microwave, even higher frequency. If it is a higher frequency, then it's possible. Okay. Nowadays there are also some group they are working on we call as a terahertz radar. So terahertz radar is actually quite close to the optical sensing already. Let me show you the frequency. Okay. So microwave is here. Terahertz is somewhere here. So terahertz is very close to infrared, and therefore it has the characteristic of radar, and also it somehow there are also characteristic of infrared or visible light. So in this region, people use the terahertz radar to do diagnostic, even to an extent of potentially, not confirmed yet, potentially is for like diagnosis of the say cancerous cell, or diagnosis of all those some disease related to the human health. Okay, at this level, and of course it also it is just sufficient to see through like human skin. Some is actually just sufficient to see through our human the cloth and also skin, so you can see the tissues, you can see the bone. The application is to replace the X-ray, because X-ray we know is radioactive, and it is actually not good after you do frequent scanning using X-ray is not good for health. But then terahertz radar, they have less issue on that. Okay, so that is one aspect. But if look at the COVID-19 situation now, for remote sensing in general, if we talk about how we can use remote sensing technologies to help this pandemic case, one area is of course we can automate all these remote sensing sensors to help us to do a more effective scanning of human body temperature. Okay, like for example, now I think there are a lot of shopping mall, or maybe those are public area. They try to do rapid scanning, but it's not that efficient because now we still use a handheld temperature sensor for us to do the scanning. So one of the possible application is actually we can use infrared imaging techniques for us to do the rapid scanning of the body temperature. There's one potential area, I think. Other than that is by using a combination of few remote sensing technology, visible optical cameras together with say some of these high-end radar system, you can actually try to track people to the extent like this person that go where and at what time and things like that. And of course to combine with all the smartphone apps, then it is more effective for us to track and know every single individual the movement of the individual. So this is actually kind of like we can use to do a control and analysis study of the spread of the virus.
Yes. So radar can be used for mobility tracking of the person.
Yes. Yes.
Okay. Another questions. I think we still have time, 5 minutes more. Another question is from Mr. Fahri. Can SAR imaging be used to model the sea, the basic of the sea? Suppose you are in the depth of the oceans, the deeper you are, the stronger underwater pressure will be.
Okay. Well, water or underneath the sea, radar normally cannot be used. The radar system, they have a limitation. So this is one of the limitation. The absorption is actually, water absorption is very severe. So normally, radar is good for say above the sea or under the ground. If it is something that not very the moisture content or the humidity is not that high. Okay, when you talk about say under the sea, so normally the technology used is actually related to ultrasound, ultrasonic technology, where it will be able, it is more effective for underground or undersea the basic mapping and so on. Okay. Radar or the microwave is not suitable for undersea mapping.
Yes. Okay. Yeah, I think your answer will also replying questions from Aflaha. Okay. So another questions is from Bintang. Can SAR or radar image be implemented in for virtual reality game with the results of image data from this world, which will be entered into virtual reality game?
Yes, of course. Now, actually, there are a lot of radar they use in virtual reality. You know, in Google also they come up with another. There are some projects, X project. If you go to Google, they use radar, and now like one of the things I saw before is actually you can the radar can detect the very fine movement of your finger. Like for example, say your finger you move like this, the radar they can send this. Okay, so basically radar is good to send a movement, a very fine movement. So what they do in the one of the virtual reality game, you just imagine you play a piano, but you are not playing a real piano. You just move your fingers. Okay, and then this thing captured by the radar, and then in the virtual reality you're actually playing, and then they give you the sound of the piano playing. Okay, and what they want to do now is actually to use this our finger signature, the movement of your fingers, to give command to the brain or the computer, or say to your home appliances, to say turn on the fan. Say for example, your hand you move like that, you turn on the fan, and then higher speed, lower speed, and then you want to say you just move like that. So you tune the volume of your hi-fi set, or you want to you just give a command, then it will turn on your TV. So this is actually coming soon. The radar try to measure or try to sense the movement of your finger, because our finger is the most flexible mechanism. Okay, and this is actually something that is in progress. By if you just use, of course, if we use optical or the image processing by using camera, can we do this? It is also possible, but the resolution is not that good. Okay, image processing, we also can kind of if we use a stereo camera, we can kind of model the 3D object, the movement of a 3D motion. But then a radar will give you a different dimension and also a very high resolution of the movement. So so it is coming, and there are some games also they are actually using a radar. Okay, just a very fine movement. Okay, you know all this the movie of Harry Potter, a lot of all those magic thing. I think is doable, or maybe we can see during our lifetime.
Yes. Okay. Thank you. So one more questions from our students here. Can UAV drone be used in military needs?
Yeah, of course. Generally, radar is used for military application. SAR, or this synthetic aperture radar, it is also meant for military application. Okay, in the past. So all the radar technology it started because of military use. Then slowly after that, only comes to say other application like commercial application. Even for computer, the first version or generation of this computer system, why they want to build computer is because they want to use for military to calculate the launching of a missile, because the calculation of the trajectory of the missile is too complex. A human cannot do this, so they build a calculator they call a super calculator to do that computing. So after that, then they come up with all this computer, and eventually it goes to the commercial or the public or the civilian application. Radar also same. For SAR, for imaging radar, all this in the past only selected or those advanced country they know about the technology, and they use for military. Okay, so because of, like, for example, spy camera, spy radar system, those satellite borne system where they know, okay, where is the target they want to launch the missile, launch the all the things. So they use synthetic aperture radar.
Okay. I'm sorry, I missed questions from Mr. Rory. So I see. So he wrote again his questions. Is there possible the radar get jamming?
Yes, yes, of course. So in the area of this radar, there's a radar, there's a jamming radar. They also have a anti-jamming radar. So all this is like fight each other. So like, for example, say your radar is used for military, you want to detect the target. Say the target is another flight jet, okay, another airplane. So you want to detect the target, of course you will send a signal. You send a signal to check whether there's any target. If there's a target, then there's a signal return. So this is the way the radar works. Okay, you send a signal, hit the target, and then you get a reflection. So jamming radar is when I send a signal, the other side, they receive the signal, they know this signal, and then they retransmit the signal, maybe like at a very high frequency, at a very high pulse, high energy pulse. They jam the receiver of your radar, whereby you cannot recover the signal. So they either use an energy to jam the signal. Another is they use a special code to jam the signal, because now the modern radar system, they also have an encryption. So you decode or encode the signal, so that the other part or the enemy, they cannot actually recover the signal. But at the same time, the other part, they can do the jamming to jam your signal, and then to make the signal which is not readable by your radar system. Then of course there also anti-jamming. Anti-jamming is they try to recover this jamming. Okay, they are another way to do is actually they put a lot of absorber, so that your signal, when you send to the target, it disappear. Okay, it will not be reflected, because of the material they use is actually cancel off the return signal.
Yeah. All right. Thank you very much. Participants are very active. Okay, but time is over. So, dear participant, please give applause to Professor Ko. Okay.
Thank you. Thank you for your time.
Okay. Okay, Mbak Ani, I will give time to you to deliver a token of appreciations.
All right. Thank you, Prof. Ko, for the knowledge that's been shared to us. And as a form of appreciation, we would like to present a certificate for you. Please kindly receive it.
Oh, thank you.
Thank you, Professor Ku.
Thank you. So how I receive this one virtually, is it?
I will send it to
We'll
you
send it to you, sir.
through email.
Okay.
Just for the ceremony.
Okay, thank you.
Thank you very
Right,
much.
before we close the today's event, I would like to ask everyone to turn on their camera for the photo session.
Okay. Please, all participants, could you please turn on the camera for having a group photo?
Yeah, by the way, we actually we offer some postgrad what the opportunity lah. So if any one of you are interested to work on remote sensing related topics or any other topics, you can also contact me later. There are some, because we also have some PhD student from Indonesia.
Nice.
So if you happen you want to find out more, maybe you can let me know. Okay. We have some scholarship also for postgrad study.
Thank you, Professor. Maybe Mas Roni, are you interested to apply PhD under supervised Prof. Ku? He just received a Best Paper Award today.
Oh, congrats.
Ronnie, who asked you the first question? Okay, please have a group photo, Mbak Ani. Could you please lead?
1 second. Okay, 1. We have another one. 2. 3. Okay, that's all.
Okay, thank you very much. Thank you, Professor Ku, for the
Thank
good
you.
job.
Stay safe.
Thank you, Dr. Fazli.
Yes.
Yeah, thank you, Dr. Nia.
Great collaborations.
Yes.
All right. So if there's anybody interested in postgraduate study, as mentioned by Prof. Ku, just not only limited to remote sensing, other programs also on robotics and communication. Please, we can communicate later.
Yes, sure. And also, if I think there are also summer school programs, right? Delivered by MMU, summer school.
Yes, exchange programs, either inbound or outbound. But it again depends on the situation.
Situations,
With
yes.
traveling. Of course, we can still do virtual ones, but not as far as going for 2 weeks.
Yes.
But of course, if we can do it physically, it will be more enjoyable.
Yeah, maybe next year. Hopefully next year situation
Yeah,
will be
maybe next
controlled.
year.
Yes. Okay, thank you
alright.
very much, Dr.
Thank
Fazli.
you.
Okay, bye-bye.
Thank you.
See you.
Ladies and gentlemen, that's the end of our agenda. We would like to express our appreciation to the speakers for the informative and interesting presentation and for all the participants. This program won't be the same without you all. Once again, thank you very much. Have a good day and goodbye.
Bye. Thank you.
Bye-bye.
Thank you all participants as well.
Okay, thank you very much. Assalamualaikum.
Waalaikumsalam.
Assalamualaikum.
When can we get the e-certificate?
Our team, will send the e-certificate through email.
Okay, thank you very much. I wish you all the best.
Yeah, see you. Thank you. Oh, have you filled the attendee list in the chat box, all participants?
I did not fill the attendance list. I do not know where to fill. Can you help me to fill up?
Yeah, we
The
already
chat box.
sent in the chat box. Ani, could you please share again in the chat box?
All right, I will share again on the chat box. Please, anyone who hasn't filled the attendance list, please fill it to obtain the certificate.
Chat box, huh?
Yes.
Yes, in the chat box.
Okay, okay. I will because I'm not very familiarized with this Zoom. Huh?
Yeah, it's okay. Oh, okay.
Where
Yeah,
is
we also had a recording.
chat box?
Yeah.
Oh yeah, yeah. I see the chat box. Okay, so I will fill up. Okay, I
Yeah.
got it.
Okay.
Okay.
See you.
See you. Thank you. Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh.